In other words, the amount of power you have to budget in order to ensure reliable communication over a wireless link. So, last time we finished up with a discussion of Rayleigh fading. And basically what we argued was this is what happens when you have, so this is in the context of multipath propagation. This is what happens when you have many paths from your transmit antenna to your receive antenna, bouncing off all kinds of random impairments in the environment, and generally there will be no dominant path in a Rayleigh environment, Rayleigh scattering environment. Something like this. So you've got this huge number of fairly scattered paths arriving at the receiver. Yes?
I just listed both of those out.
Okay, great. So tutor, tester to make sure you can use MATLAB. So if you can use it from red, you can use it in Prism. So yeah, that'll work. Thanks. So the idea is lots of random paths. They're bouncing off random scatters in the environment. They all arrive here with random path lengths, random phases. They all combine here, and the question is, what's the amplitude? Well, clearly, because all of these are random, the signal strength at the receive antenna is going to be itself a random variable. So what we showed was you can model the received signal as something like A sine 2 pi ft plus theta r. Theta r is just the phase changes observed at the receiver, and A is the amplitude. What A turns out to be is a Rayleigh random variable, Rayleigh distributed. And we explained a little bit why that is, although it's not terribly important. But what we did see was that most importantly about this, the probability that this amplitude A is less than or equal to some value that I give you, let's say A star, is equal to 1 minus E to the minus A star squared divided by 2 sigma squared, where sigma squared is equal to the average power. Question?
There were a couple of questions T was not able to explain, and this was one of them. He said it's just minus A squared, minus A is not a squared. And there was another question he didn't have explanation for. That was the bandwidth question.
Okay, here it's possible the error was in the solutions that I gave him. It's A squared. It's definitely A squared. That's the other question. Send me an email. I'll answer. Okay, so let's have a quick example. Let's say the average power is 1 watt. What is the probability that the amplitude is less than 1? Okay, well, all we have to do is take a look at our handy formula here and plug everything in. So probability that the amplitude is less than 1, less than or equal to 1. So here I write less than 1, here I write less than or equal. There's not really a difference in this context. So probability A is less than 1 is equal to 1 minus E, the minus A star squared. What's A star? It's 1, so A star squared is also 1. So 1 minus e to the minus 1 over 2 times sigma squared. Sigma squared is the average power, which is 1 watt. So we end up with 1 minus e to the minus 1 half. And you can just plug everything in and get an answer for that. Okay, another flavor of this question might be, what is the probability that, so we know the average power is 1 watt, but if I look at the channel at any particular time, there will be an instantaneous power. So I can measure the instantaneous power. What is the probability that the instantaneous power is less than 4 watts? Okay, so again, difference between average and instantaneous. The instantaneous is the outcome of the random variable you observe. So for instance, if you have a die, and you roll it, the average outcome, I think the average outcome is 3.5. But if you look at it at any particular time, it can take any value from 1 to 6. So the actual outcome is the random variable. So how would we approach this question? We have instantaneous power down here, but what we really need in order to plug into our formula is A star. How are those two quantities related? We talked a little bit about this last time. Yeah, so remember that power is the square of amplitude, generally. So if we say the square root of 4, we get that A star equals 2, and therefore the answer to this problem is the probability that A is less than 2, which is equivalent to A star squared being less than 4, is equal to 1 minus E to the minus 2 divided by 2 sigma squared. Sigma squared is still 1. So this is equal to 1 minus E to the minus 1. Questions on that?
A star is instantaneous power?
A star is the instantaneous amplitude. So how is amplitude and power related? In this case, we're just going to argue that power is equal to amplitude squared. It'll work out.
It's the same chance.
Actually, yeah, you're right. You have a point. So it would depend on the actual structure of the signal. In this case, we'll just say, let's see, amplitude squared. Okay. So let's talk a bit about